This is section 3.2, inference for a single quantitative variable. So first, look at the learning objectives. You'll notice that it seems very similar to what we've been doing for proportions. Basically, everything we just learned about proportions and sampling distributions, we're now going to learn for sample means. Okay. So to start, let's just remember a lot of these first things are a review from section 3.2, or sorry, see section 1.2 on how to describe variables. That's when we first talked about histograms and dot plots and means and averages and medians. And if you forgot anything about like how to find a median, go back to section 1.2. Okay, so remember, a quantitative variable is when we measure things with numbers, and we summarize quantitative variables with the mean and standard deviation. So we can have our population parameters. Mu is our population mean. Sigma is our population standard deviation. So let's make ourselves a note. This is mu, and this is sigma. Those are Greek letters, because we use Greek letters for our parameters. Mu is our population mean. Sigma is our population standard deviation. Okay. For our sample statistics, we use normal letters, but often with some fancy symbol. So this one is X bar, it's for our sample mean, and S is just S, okay? Nothing very fancy about that. S is our sample standard deviation. So remember, we want to be able to describe distributions. So to describe a distribution, we look at the shape, center, and spread. We also want to look for any unusual observations or outliers. For quantitative variables, we use histograms or dot plots to look at the shape. We describe the center with the mean or median, and we can describe the spread with standard deviation, range, interquartile range, etc. There's a lot of things we can describe it with. We're mostly just going to use the standard deviation every time, just like we usually describe the center with mean. So shape and center, remember we talked about skew to the left and skew to the right. So you have something that's symmetric, where it looks kind of like the same on both sides. This one's also bell-shaped or normal, but you can have other symmetric options. Skew to the left means it has a long left tail. And skew to the right means it has a long right tail. And back in section 1.2, or if you're looking at your diagnosis section 0.2.5 on page 15, you'll see where we actually discovered if it is skewed to the left, then the average will always get pulled towards that long left tail. So the average or mean is going to be lower than the median. Whereas if you have something that's symmetric, the mean and median will be about the same. But if you have something that's skewed to the right, the mean or average will get pulled towards the long right tail, so the mean will be bigger than your median. So on the homework and exams, I could give you something, say this is right skewed or this is left skewed, and say should the mean or median be bigger. So just remember, the mean always gets pulled towards the long tail, so then you can like draw out a picture and figure out where the mean and median are, and you can answer the question. So here's some backpack weights of 99 students at Cal Poly. This data is in the descriptive statistics ISI applet. So if we were to pull up our applet, I go to ISI applets, I want quantitative, I want descriptive statistics. And most of the applets have some data sets already built into them. So I want to do the backpack data, and I click use data. Okay, everything that I need is in here. You can see here's my data set. Let's first describe the shape of it. I would say this is not symmetric. It seems to have a long right tail. So I would say this one is skewed to the right. What else could we describe though? We could say something like most of the values are between, let's see, what are they between? Looks like most of them are between like 1 and 25. Do you see any unusual values though? Looks like this value way up here, that does seem pretty unusual. I say you have an unusual value at 35 pounds. Now, one of the things we're supposed to do when we have quantitative data is include our units. Okay? You'll notice I'm not very good at doing this at all. Okay, but we should always include our units. If we were in class, I'd tell you to remind me, but we're not. But you should try and include your units as a habit. Okay, just looking at this, could you try and guess the mean and median? So let's actually do the median first. We know the median means half the data to the left and half to the right. So I could try and eyeball it. I don't know if I can eyeball it. Maybe like somewhere around here. I'm not quite sure. You could also count it. I think it's kind of mean to actually make you count when computers can do it, but I have seen problems on the homework or exam where she might actually ask you to count. So you know there's 99 students, so half of that is like 45-ish. So you could just start counting like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let me pause it and count 40. Okay, so we said half of 99 is about 45-ish. If I counted correctly, I think my 45th one is about here, so it looks like about 10 pounds, so I'm going to guess 10 pounds. I'm never trying to get you to be exact enough on the test that if you accidentally counted off, or you accidentally did like 10.1 or 11 or 9, like you're going to get the right answer. Okay, I'm not going to be that picky on the test. Your choices would be like, is it 3 pounds or 10 pounds or 15 pounds or 25 pounds? And you should be able to tell it should be close to 10. Okay, once I know that that's my median, I can figure out, okay, well, here's my median. I can figure out where should my mean be. We said it's skewed to the right. It has that long right tail. So my mean has to get pulled this way. That long tail pulls my mean that way. So just trying to eyeball it, like where would my tipping point be? I'm going to guess like here. Maybe, so maybe like 12. If I was going to guess the standard deviation, again, on the test, this is always multiple choice, and your choices should be far enough away that you should be able to guess pretty easily. But if you remember, most data should be within 2 standard deviations of the average. Okay, so if I wanted to get from 10 over to 0, in 2 standard deviations, how big should each standard deviation be? Like this is 1 standard deviation, this is 2 standard deviations. So to get from 10 to 1, you'd have to have about like 5, 4.5. Or if I wanted to get from 10 to 25, then like this is 1 standard deviation, this is 1 standard deviation. So to get from, actually not from the median, but from the mean. So to get from like 12 to 25, you need 2 standard deviations, so 12 to 25, like 12-ish, I would guess, would be each standard deviation. Sorry, you're going a distance to 12, so I'm going to guess like 5 to 6, maybe. Okay. Again, multiple choice. If she gave you a number, let's try 5, and let's say we think our mean is 12. I could do like 12 plus or minus 2 times 5. Is, let's see, that would be 2 to 12 within 22. Does that include most of your data, like 2 to 22? It's not quite, but it's pretty close. Like I would guess 5 could work. It couldn't have been a different value, like it couldn't have been 10, because then I'd be way too far away. Now this might show up on the homework, definitely not exams. The median and mean though, like you won't even have to guess the mean, but she could ask you what the median is and you just actually count. Okay. Now let's go back to the applet. So you can guess on there, or you can ask for the actual values. Okay. So my actual, you can actually see it here. My actual mean is 11.7. My median is 11. I guess I must have actually counted wrong, but like I said, you don't have to be very exact. And for my SD, my actual is 5.76. Now this next question, if we remove the student with the 35 pounds, so this student up here, if we removed him, what would happen to the mean and median? What about the standard deviation? So this is more just using it logically. So if I took this out, so just imagine covering it up completely, then all of my data would be much more consolidated. I feel like my average would go down because there's not that point pulling it way up. So my average would decrease. What about your median though? So you already have 99 points and the median is just half to the left and half to the right. If you only take out 1 point, basically you just move like from where you are down a point or up a point or whatever it might be. And so I feel like your median's not going to change very much. Maybe a little bit, not very much. So the median would be about the same. But looking at the standard deviation, if you took off this point right here, then everything gets much more consolidated, and I would think your standard deviation should be smaller. Now the cool thing about the applet is you can go to the applet, you can actually click on that point. Okay, so now I've clicked it, it turned red, look, this new thing pops up, click dot to observe the observation, selected the 35 pounds, I can delete it. Now my mean is 11.4, so I was right, that one went down. My median stayed the same at 11, and my SD went down to 5.2. Okay, so now we're going to discover the central limit theorem for sample means. So we had a central limit theorem for proportions, now we have one for sample means. So the Gettysburg Address is an example of a population because we have all the words from the address, and we're interested in studying the lengths of the words. So the average length of all the individual words is 4.295 with an SD of 2.12, and there are 268 words. So this is a histogram of our actual population. Let's label the given numbers with the correct symbols. Are they parameters or statistics? Well, this is for all the individual words, so it's for our population, so these are going to be population parameters. So my mean, we're going to use mu equals 4.295. And my SD, we'll use the sigma. Sigma equals 2.12. Now let's see, is the population normal, symmetric, skewed? If you look at it, it's definitely not symmetric, so it can't be normal. It kind of looks like it has that long right tail, so I would definitely say skewed to the right. Okay. And I didn't ask you here, but I should have. I should have asked something like, is the mean bigger, the median? So if I was just going to guess, like if I guess that this is my median, then my mean would have to be farther to the right because the mean's going to get pulled to the right. So the mean should be bigger than the median. So now I want to take random samples from the Gettysburg Address and find the sample averages. We can use an applet to simulate drawing 50,000 samples of size 10, 30, and 100 from the population. So we're going to go to eyesight applets. We want to go to quantitative and one mean. We use this drop down to select Gettysburg. Click use data so you can see your population matches what we thought it should. Show sampling options. So it's different than the proportions applet. You actually have to do show sampling options. Ignore the stratifying cluster. That's if you're getting much more technical than we get in this class. We can do 50,000 just for fun. You could do 10,000. And we're going to different sample sizes. So first I'll do a sample size of 10. Let me make this one bigger. So you'll notice that my population, now it has these little blue dots. It's saying like, these are the actual observations that we sampled are those little blue dots. This plot right here is your most recent sample. These little blue dots are the actual values that were in your sample. And this little triangle says your sample average for that sample is 4.2. And actually, if I only do one sample at a time, let's reset, and I draw the sample. So here's a different sample. There's different blue dots. Different blue dots here, a different sample length of 4.5. And you can see that there's one sample mean of 4.5. If I draw another sample, I happen again get another sample that had a sample mean of 4.5. Now I got another sample that was actually all the way down that had a mean all the way down to 3.7. Because it knows the blue dots, it just happened to pick blue dots that were lower down. Okay. Draw another sample. So now my blue dots are more spread out. Now my sample average is 5, and it puts a dot for my sample average. So now let's do like 50,000 of them. Okay, I draw my samples. Okay. So here's my sample means. Looks like I go from about 2 to 7. Let's change the scale to fixed. Because now, what if I wanted to do a different sample size? And I don't remember I have on my notes, so let's say 100. Now it's drawing a lot more blue dots because there's 100 blue dots in each of my sample of a size of 100. Now when it did the sample means, notice how much I shrank. Okay, before I had a much bigger, wider distribution. Okay, now my distribution is really skinny. So skinny, in fact, that because I changed the scale, it doesn't look like it's normal. So let's change that. My scale still looks kind of weird just because I didn't like that I changed it in the middle of it. Okay, so again, smaller standard deviation when I have a bigger sample size. Let's go back to our notes. So here's what I got when I drew out a sample size of 10, a sample size of 30, and a sample size of 100. Okay, but they are on different scales. So when we look at a sample size of 10, it looks like they're probably centered about like 4.3-ish. So using the applet, it was 4.295. So just like before, actually you don't even have to click summary statistics. It will just always tell you the mean, SD, and the number of samples. Okay. So we have our mean of 4.2, SD of 0.65. Now for sample size of 30, it looks like I'm still centered around that, like 4.3, so my mean, yep, 4.296. But my standard deviation, notice my standard deviation got smaller. And the scale changed, so you do have to pay attention, because it doesn't look like it changed. But my standard deviation got a lot smaller. And the sample size of 100, we're still centered right there, about like that 4.3. My standard deviation, though, got even smaller. So if they're on the same scale, you would have noticed that my distributions were getting skinnier and skinnier. Okay. If you look at the shape, they all look actually fairly normal. So as the sample size got bigger, what happened to the shape? So as it gets bigger, it will look more and more normal. But really, even at a sample size of 10, it was pretty close to normal. I couldn't really tell the difference. Okay. The center stays at mu equals 4.295. Give or take a little bit for just simulation rounding. But my spread, my standard deviation, got smaller. So let's use another applet to create any population we want and then take samples of different sizes. If we take thousands of samples and look at each sample average, we get the simulated sampling distribution of possible sample averages. So this applet is pretty cool. So you start with the parent population, okay, and then you can say, I want to pick out the means, find the sample means. You can change the sample size to like 25 or something. And you can do 100,000 samples. Notice it looks like a normal distribution. It's not great because they didn't put very many pixels into this, so they need to do a lot more pixels. Okay, and then you can tell it looks like a normal distribution. The cool thing though is I can come in and I can change this to a right skew distribution. I can even leave this weird hump in there. Okay. And then I can say mean, and I can do a sample size of like 2 and do it. So when I have a sample size of 2, then my sample means they still look right skewed, but they're a lot more normal than they were. And then if I do my mean and I do a sample size of 25, notice it looks pretty normal. In fact, it would look a lot more normal in this, but they didn't put in very many pixels, so it doesn't look right. Okay. But even if you start something that's very right skewed, by the time you get to sample size of even like 2, it looks a lot more normal. By the time you get to 25, it'll look pretty normal. I can try and make this as weird as I want. I can even make a distribution that looks like this. And let's try and see what happens. Oh, I do have to reset. Okay. So at a sample size of 2, my sample means don't look normal, but you can tell they're trying to look more normal. Let's try for 5. At 5, they're looking kind of normal, a bit skewed, but kind of normal. But by the time you get to sample size of 25, it looks really normal. So coming back, so these are 3 different populations that I went through and did this for with a better app. The app is gone now, but this was a better app where it actually had more pixels. So for population 1, it started off normal. Okay. By the time I got to sample size of 2, my sample means are normal. Okay. Sample means at 5, 10, 30, they all look normal. My standard deviation gets smaller and smaller. They get skinnier and skinnier, but they're normal for all of my different sample sizes. Okay. Population 2, though, it was very right skew. At a sample size of 2, it's still skewed. At a sample size of 5, my possible sample means are still skewed. At a sample size of 10, maybe a tiny bit skew. For sample size of 30, it's just going to be normal. Okay. Population 3. This one was a fun one that I just did for fun. This one actually has 3 modes, like 3 major peaks. By the time you get to sample size of 2, then my possible sample means looks weird. You can tell it's trying to get back to more normal, but we've actually got like a lot of humps there, a lot of different modes. Okay, by the time we get to sample size of 5, then my possible sample means are still not normal. But they're getting pretty close. Isn't that crazy? It only takes a sample size of 5 and they're already trying to be normal. At a sample size of 10, we're like at almost normal. And by the time you get to sample size of 30, then those possible sample means are very normal. Which is so cool. This is why this central limit theorem is so famous, because it's saying you can take any population you want, and by the time you get to sample size of 30, then your possible sample means are going to be normal, which is so cool. Okay, so once we get to a sample size of 30, we can guarantee that the possible sample means will be approximately normal no matter what population we started with. So the central limit theorem says, again, if the sample size is at least 30, then the sampling distribution of all the possible sample means will have a shape that's approximately normal. And the mean of all the different sample means will just be equal to the population mean. So the mean of all the x bars is just mu. And the standard deviation of all the x bars is just sigma over the square root of n. And remember, as the sample size gets bigger, the standard deviation of x bar of all the different sample means gets smaller and smaller. The reason why is the standard deviation is calculated by this sigma over the square root of n. So as n gets bigger and bigger, mathematically, the entire number has to get smaller and smaller because you're dividing by a bigger and bigger number. Now, the interesting thing is, if the population started off normal, then the distribution of the possible sample means is approximately normal for any sample size. That's what we saw here in population 1. Because it started off normal, then my sample means look normal for every different sample size, which is pretty cool. Okay, so when can you use the simulation and when can you use the theory-based normal curve? So if our sample size is big enough, at least like 30, then the sampling distribution of all the possible sample means is approximately normal. That means we can use the normal curve to find probabilities. But if your sample size is not big enough to use the theory-based normal curve, you should still use simulations. So for example, here's a data set for the year of pennies in a large collection. Let's say I want to take a sample of pennies and look at the average year. So we go back to our ISI applets, quantitative, 1 mean, pennies, so you can select it, it's already in there. We go to pennies, use data. So always check, so I clicked use data, it didn't actually look, because I'm like, oh wait, that looks the same as what it was before, that doesn't look like what I was supposed to get. Let's try again, use data. Okay. So here's my population for all the pennies. We have a mean of 86.7, standard deviation 9.6, and it is definitely left skewed. So we would definitely describe the shape as left skew. So we want to use the applet to find the sampling distributions for sample sizes of 5, 30, and 100. But they're from different scales, so which one's which? Well, let me show you how you put it in first. So let's say we want 50,000 or 10,000, whatever you want for your number. And then you can put in your sample size. So let's say I want a sample size of 5. We can draw our samples. Remember, this one will be, these little blue dots are just your individual samples, so you need to go over until you get to your sample statistics. So notice when I do a sample size of 5, I'm still skewed. That makes sense from what we just learned, right? When my population was skewed and I take my sample means, if I have a small sample, it's still going to look kind of skewed. Okay. If I wanted to do a sample size that was bigger, like for 100, I can draw my samples and wait. And now notice it doesn't look skewed anymore. It looks pretty normal. So let's come back to our notes and see if we can figure out which distribution went with which sample size. There's 2 ways you can figure this out. Okay. The first one is that bigger sample sizes are more normal, not skewed. And bigger sample sizes have smaller SD. So let's look at our examples here. See which one's which. This one looks kind of skewed, don't you think? So that one looks skewed. This one's maybe a little skewed. maybe. This one looks pretty normal. But now let's look at the SDs. They're very nice to give us the SDs. So this one has the biggest SD. And let's see, that's medium. So this one is the smallest SD. So now that we know that the most normal has to be the biggest, smallest SD has to be the biggest. So I'm going to say that this one is n equals 100, sample size of 100. This one has the medium SD is medium as far as like most normal, so I would say this is a sample size of 30. And this middle one had the most skewed, the biggest SD, so it has to be the sample size of 5. Now we could use the applet to find different probabilities. So this one says, like, let's use the applet to find the probability we get a sample mean x bar less than 84. So I want you to just look at it first. If this is 84 right here, okay, or here's 84, or here's 84 right here. Okay. So for a sample size 5, the chance to get a sample mean of 84 or less, that seems pretty big, don't you think? But when we have a sample size of 30, the chance to get a sample mean of 84 or less, that seems a lot less. There's a lot less area in there, right? And for a sample size of 100, the chance of getting a sample mean of 84 or less seems almost non-existent, right? So we can see we're much less likely to get a sample mean of 84 or less for a big sample size. For a small sample size, we have a much bigger spread. We're likely to get a lot more different sample means. Let's use the applet though. So sample size of 5. Okay, so I'm doing 10,000 samples, sample size of 5. And here's my nice sampling distribution. And I want to come down here to count samples. We actually want less than or equal to 84. We can count. And it's a little bit different than the proportions. It doesn't tell us our p-value up here, but it does tell you the p-value down here. Your count is 2,631 out of 10,000 samples. We're had a sample mean less than 84, and that p-value is 0.2631. So 0.2631. I can also click overlay the normal distribution. That will give me my theory-based p-value, which is labeled for you as 0.2621. So now we want to try that with a sample size of 100 instead. So we come back, we change our sample size to 100. We have to draw new samples because we have different sample sizes. Look how much it looks like a normal curve. The normal curve is still overlaid. We want to count samples less than 84. So you can see our p-values are 0.0017 for the simulated and 0.0022 for the theory. So 0.0017 and 0.0022. All right. Sorry, I paused that, and I'm not actually sure where I paused that. So just to make sure, we came back up to our original population, and we wrote down our mean standard deviation using our Greek letters. So mu is our population mean, sigma is our population standard deviation. And then coming back down, so my mean of all my x bars is mu, so that's 86.736. And my standard deviation, my x bars, is the sigma over square root of n, so 9.608 over square root of 500, and I got 0.43. And we said, if you wanted, you could just go to the simulation and you could put in a sample size of 500, draw your samples, and it will tell you your mean in SD. Now we're a bit off just because of rounding, because it's a simulation. Not a big deal at all. Okay, it would still be close enough you get the right answer on a multiple choice test. Let's see, what if we switch from a sample size of 500 to a sample size of 15? So what would change? Okay. So let's think about it this way. If we're at 500, I might need to make that skinnier. Let's say this is what we found for 500. If I wanted to imagine what it would look like for 15, it would have to be much more spread out, right? Like bigger sample sizes have smaller standard deviation, so bigger ones have to have less, or bigger sample sizes have a smaller standard deviation. So smaller sample sizes have to have a bigger standard deviation. What about the shape though? 15 is less than 30. So we are not guaranteed normal. Now, some populations, 15 might still be big enough to look fairly normal. We could try it. We could put in 15. We can draw our samples. And notice it actually still looks pretty normal, but we're just not big enough to be guaranteed that we would be normal. You can also see that using the simulation, we can see that the mean is 86.716 and the standard deviation is 2.464. So those are my simulation values. Now, we would have expected the mean to stay the same. So the mean stayed the same because we realized that no matter the sample size, the mean has to just be equal to our population mean mu. So my mean of my x bars, oh, I'm sorry, I just wrote x's. Those are x bars there up on our notes. The mean of my x bars is mu, so it's supposed to be 86.736. Okay. But our standard deviation, we realized that my sample size is smaller, so my standard deviation has to be bigger. You could actually find it, the standard deviation of x bars is equal to sigma over the square root of n. So 9.608 divided by the square root of 500 gives me, sorry, not a sample size of 500, we have a sample size of 15. So if you divide by 15, you get 2.48. And again, just different because of the simulation. Okay, last example here. The average wingspan of an American robin is 35 centimeters with an SD of 2.5. Let's always write down what they gave me. That sounds like it's for all American robins. It doesn't sound like it's a sample. It sounds like it's a population. So for my population, we have a mean of mu equals 35 and a standard deviation of sigma equals 2.5. Having that written down helps me know what's in the problem. It helps me plug things into my formulas. If you want to take a sample of 10 birds, what do you expect the sampling distribution of all the possible sample means to be? So we're going to take a sample of 10. Well, our shape, n equals 10 is less than 30. But, so we wouldn't be guaranteed to be normal, but notice up here it says wingspans are normally distributed, but the population is normal. So the x bars will be normal. So even though my sample size is small, because my population is normal, my possible sample means will also be normal. Now your mean of your x bars is just equal to my population mean mu, which is 35, and my SD of my x bars is equal to sigma over the square root of n. So sigma is 2.5 divided by the square root of 10, which gives me 0.79. Now, if you switched from a sample size of 10 to a sample size of 100, what would change? Okay, so the shape will still be normal. Okay, normally it would be like even more normal, but my population started off as normal, so still normal. Okay, my mean should stay the same because it's still going to be mu equals 35. But my standard deviation, without actually calculating, but you could calculate if you forgot. Remember, if this is n equals 10, then we switch to n equals 100, it would have to be even skinnier, right? So we know bigger sample sizes get skinnier, so my standard deviation has to get smaller. And just for comparison for you, we've now learned about sampling distributions and the central limit theorem for proportions and means. So let's just go through those to help cement it into our brain. So for our sampling distribution for p hat versus sampling distribution for x bar. So we use p hat, our proportions, when we have categorical variables. We use x bar, our sample means, when we have quantitative variables. Your statistic for proportions is your sample proportion p hat. For means, it's your sample mean x bar. The center of the sampling distribution, or the mean of all the possible p-hats, is pi. The mean of all the possible sample means is mu. So population proportion, population mean. The SD of all the possible p-hats is the square root of pi times 1 minus pi over n. Whereas the SD for all the x bars is just sigma over square root of n. Different looking formulas because we're doing different things. The shape for both of them will be approximately normal, but your validity condition for how big your sample size has to be for these sampling distributions to work. For proportions, you need your successes and failures to be at least 10. So in other words, like n times your pi, n, your sample size times your population proportion has to be at least 10. And your sample size times 1 minus your population proportion has to be at least 10. So if you like formulas or if you just like it in words, either way, your successes and failures have to be at least 10. For sample means, though, your sample size just has to be at least 30. Much simpler.